Hello. After seeing some really exciting stuff that people can do with Flink around Flink so far this conference, I'm going to kind of show some boring stuff. What I mean by that is we've seen like dynamic code as a configuration being passed by Ing Bank. We saw optimization of the execution engines by Alibaba Group, and we saw ACID transactions by data artisans, which are all super exciting, interesting ways to really push Flink. I'm actually going to cover something rather different. I'm going to cover using a source and a sink, and what you got to do to optimize your code to really make that work well. And that's where this kind of real-time and noisy data, this worked just a few seconds ago. Probably I just need to activate. No. There we go. So the use case I work for a company. We make map data. That's our core business. We're trying to make the world have safer roads and easier to navigate roads. That's what we do. We've been doing it for 25 plus years. And maps were traditionally pretty static, and we're trying to make them way more alive now. And that's where a stream processing framework like Flink works beautifully. Increasingly, if you look at an automobile, we have something called the CAN bus, which is the internal sensor bus within a car. And a modern car, coming out in the last couple of years, has about a gigabps worth of traffic going around that. And we now have a connected bus where we can start uploading some of that up to the internet. Nobody's uploading a gigabyte per second up to the internet out of your car yet, but we're beginning to look there, and how do we kind of make that work? So what I want to describe is some of the use cases we have where we get conditions like, is a tire slipping? Is that getting slippery? Is there a broken down vehicle? Did we see an airbag go off? Is there a parking spot? Increasingly, those collision detectors on the side of the car actually doesn't just tell me, they actually can search out about 5 to 8 meters into the side. They're constantly running, and they can actually detect whether there's an empty spot there. And this is all cool data, but what can we do with it? And that's probably what I'm going to talk about. I give a high-level example here where you kind of talk about, we'll go through some geometry, we're going to go through a map matcher, we look at reference paths, we do our customized filtering, what type of sensor did we get, we classify it, we associate it with a map, and that's kind of how we go from there. And so we're trying to build these living maps. And again, just getting all that data from those vehicles and referencing it to something. And this is the problem where we start talking about messy data, is the data, GPS coordinates suck. In practice, they don't show up where they said they are. In cities, they're even worse than in the country. You get the bouncing off of the wall, and you wind up in the middle of the block over, as opposed to actually on your block. And so what I'm going to discuss is some of the ways you filter out that data fast. And that's where the real time comes in, is I want to talk about how do you really make that. And so part of what we're doing it here is we have this thing called the Open Location Platform, where we're trying to let our customers build their own maps. They could build these live layers, they could be building static layers, using Here's platform and the technology that we're trying to make a little bit easier for the rest of the world to use, and in fact, our own teams. And we do manage Flink, and we run it, and we integrate it with Prometheus, and we have a whole managed service, and I'm not going to be talking about that today. I'm going to talk about a little tiny bit of the platform, which is how do you add location context to your data, and what techniques can we get to really do that? And so I'm talking about stream processing strategies. When we're talking about stream processing, we want low latency. We want data. I want to have that signal come in. I want to do my processing on it, and I want to get it out. I want to get it out really, really fast. And I want to reduce the engineering load, because half of what makes anything expensive these days is updating it, modifying it, figuring out the next use case. So I'm going to go over 3 really simple, basic techniques, and I'm going to go into how we optimize them for some particular use cases of pre-computing, because a lot of data, you know what you're going to be doing ahead of time. Deterministic data access. When you know what your data is like, that will guide you in how you set up your pipeline, or how you set up, sorry, that's our internal term for it, how you set up your Flink processing so that you're putting the right data onto the right node, and that you're actually able to use the caches that the hardware gives you to actually take advantage of that. And then some of what we did of saying, how do we produce algorithms which are optimized for infrastructure, but we still let our users extend them. And so to go through this flow, being here in Berlin today, I decided to go to the Trabant. I don't know of any connected Trabants out there, but maybe in a couple of years. We've got the CAN bus. It sends up sensors. In our case, we stick it into our own stream layer. It's Kafka with our own added security layer on top of it. We send it to our processors. I have 2 processors just in kind of this example. There can be more, but I have these 2 Flink processors. And what I'm actually doing is I'm storing bits of the map in the RAM of those processors. And I'll come back to why I need reference data as quick as possible, and why I can partition the world in a reasonable way. And I start with a map, and ultimately the source data to my map is measured in a couple petabytes per quarter, meaning it's growing by a couple of petabytes per quarter. And I don't want to put all that data down into the processing, so first I take my map, I funnel it down to the only attributes that I really care about. I deal this within a batch, and I update the reference of the world roughly daily. That's a pretty good frequency. The world does change. I don't need to mention that I don't have a lot of confidence which roads appeared or disappeared in less than a day. But then I kind of want to, and so I'm going to update my Flink job. I'm going to update the data set in Flink in RAM daily. But I'm going to get these sensors coming out of the car. They tend to batch them within seconds. But I've got a lot of cars. I don't just have 1 or 2. I've got hundreds of thousands that are already pushing data into this platform. So then I'm accessing that in milliseconds. It goes through Flink. I want it done in milliseconds. I want it out again. I put it into a queue of these categorized, what is the world? And then the car is going to pull it in. The mechanisms by whether a car pulls it in directly by a pull versus a push varies from manufacturer to manufacturer. But I generally am looking at that kind of in the seconds range. One thing said I wouldn't cover our abstraction around Flink a whole lot, but it helps people have a little bit better understanding as I go through this. So the way we think of it is we create an object that we call a pipeline. It's a processor. Our processor called a pipeline. Then we create a template within it, which includes a jar file. It has its own unique ID. We happen to be able to support both Flink and Spark for streaming. We highly recommend everyone use Flink on our platform. And we have a lot of other teams that are into a set of libraries that work better in Spark, so they use that. And then we create a pipeline version. And that version, we can then do some things to it. We can activate it. We can cancel it. We can pause. We can resume. We can upgrade it. Upgrading, again, the notion is you produce another template, you can suspend one, and we save out the state. And we actually hide all of that for our users, so they just have a piece of code. We use Flink's nice ability to save out state, and you launch the next version, it absorbs the state from the previous version. This is just, again, a little bit of context as I talk to how we do it. So now I want to talk about our implementation strategy. So I had those high-level objectives of what it is I wanted to do. So I want to optimize my data for the use case. I don't need all that data. And one of the ways that I do that is I can say, I represent normally the world when you think about producing a map or whatever your data set is, you often have a version of it that's optimized for editing. Just because something's optimized well for editing, managing, keeping its life cycle in state, doesn't mean it's good for reading it. So a good example here is I represent the world in blue on that upper right-hand corner as what I call segments. I have a unique ID. It represents a piece of continuous road. It goes from one intersection to another. I know it has a house number. I know that it's within the city of Berlin. I have a lot of attributes about it. I don't care about any of that when I'm trying to just figure out where on the map does something Where was that event when someone had an accident? I want to get to a point, but I want to get to a point on a street because I know that the car is traveling on streets. So instead I say, you know what? I don't want this segment with all those. I throw that out. I need a vector. And I happen to know that when I stored my street for editing, I said it was 2 ways. But if I want to match it, I want to convert that into vectors so that I can look at the direction they're traveling, and that'll help me choose the right place to figure out where was the data. And a vector is a really small entity to store in memory, so I can match against it really nicely. Another key thing is I key by something called map tile. Another nice thing about working in location is, guess what? We don't teleport. I don't drive down this street, wind up in Portland, Oregon, then wind up in Tokyo, and make my way back. I have to go continuously from one spot to another. This is also really nice because it means that my caching strategy works really well. Because if I start downloading nearby data from the first point that I saw, I'm going to be getting the next set of data. Whether your data specifically is location data or not, you can often find patterns within your own data to make sure that you can aggregate it into a group that fits nicely for your access pattern. Doing this provides enormous latency savings on when you have to access data frequently. So in our world, we can say, in the world of map tile 0 and map tile 1, map tile 0 happens to be North America, and I have a picture of that next. Map tile 1 happens to be Europe if I divide the world only in 2. And in this case, I can get this data down to around, in this optimized, indexed format, I'm down to around 4 gigabytes, which I can put in a single processor. That's a reasonable amount of referenceable data. The next thing is, how do I make my code extensible? So to explain my colored dots, which I'll come back to a little bit later, yellow is the sensors that I actually receive. They go back and forth. And then you have circles and triangles, 2 possible roads where that data might be. And so our logic is we think of a function of emission probability. I mean, it's a hidden Markov model, classic algorithm. And we make sure that the implementation of those sub-algorithms, we let our individual customers do, because that is a good level of abstraction. That's where the custom logic comes in. So this is the map matching code that I'm kind of talking about. And this is using our platform, and that's pretty much all there is to it. The data client goes and it gets the optimized map. We have this thing called the data client, which gets our stream, and it makes it our source in Flink. We parse some SDII, which is a standardized format for these sensors that come out of cars. And we take it from Proto, make it a Java object, and then we send it through a map matcher. And you'll see the word path map matcher. And this, again, is another interesting strategy when looking at various types of data. We happen to know that your chance of getting the right answer on any point is going to be dramatically higher if it's a part of a path. And to kind of give you that example both on what is SDII and what does it mean for a path. So if you think of this, in this example, the red dots are the actual GPS sense data, and then you can have some different ways of saying how am I going to attach that not only to a map, but into a lane, which is where that car is going to be. And the fact that I actually have seen multiple of them gives me a different idea that they're probably in a row as opposed to being separate. And again, you'll often see these in other kind of fraud use cases or others. You expect data set to be nearby. And if you optimize for the most common set, which is where they're near, you're going to get a lot better latency and performance out of your system. The other thing that's a little bit frustrating for those of us who wish we just got data that was, hey, I care about these points and these values. Great, let me put it together. That's not the way I get the data out of a car. Instead, I get a timestamp and a GPS coordinate. Okay, that's reasonable. What if I wanted to know what the slope was? What if I wanted to know the wheels were slipping? All I get is a timestamp and an event that says the wheels were slipping. And the timestamp for when the wheels were slipping doesn't align to when I had any GPS points. It's somewhere in between. So this again means that to produce the type of data I actually want to provide my business logic on, where is the slippery spot? I've got to do some basic DB scan clustering to figure out where that is. And that's the default implementation that we offer in our platform. Again, you can replace it with something else, but you can say, okay. And so this is just where I'm talking about this example. I'm sure you have the same thing with your own data. You have those implied data, you cluster it together to build the next stage in your stream processing. So what do I do with this optimized map? Let me tell you a few of the dirty tricks that we do. So to understand what map matching is, what we're doing is we're going through all the possible roads that could be there, and we're looking at what is the probability on that piece of geometry that that point might have been there. So we are hitting that representation of the geometry thousands and thousands and thousands of times per point to be able to find the shortest distance and the highest probability of that. When we have that type of access, guess what? We're getting actually into L2 cache on the CPU. Makes a big difference of why do we do it. We also have found that we went to using most of the code example that we have in most of our libraries are Scala. We wound up with unboxing problems when we use Scala. So we tend to use direct references to Java integer arrays. So we do not unbox the data, and we have way better garbage collection. This reduces our latency once again and keeps the performance up for trying to do all these scans on data. We also add the attribute indexes. So we have our array of our geometry and what our attributes as a nice integer array, and then we've added additional indexes to those locations to be able to make hunting for them in relatively constant time, just to be able to get through there. And so again, we scan a lot. We really do. And again, we're trying to make it so our stream processor does as little as possible and invest ahead of time in how do we kind of optimize that. And yeah, when I look at this, I've seen use case, one of our customers came in and we performed about 2,000 times faster than they're kind of grab some map data from an open map data provider, load it into memory, and provide the same algorithm that we're doing. They were just using the hidden Markov to look for it and do the map matching using the standard emission and transition algorithms. But they just took the raw data. The simplistic approach, yeah, can be 2,000 times slower, which adds up to a lot of money pretty quickly if you're processing large quantities of data. So what is map tiling? I mentioned this briefly before. What we do is we have a partition at arbitrary depth. So we have a binary way of representing where any particular square of the Earth is. We cut it into a number of different segments, 0, 1, 2, 3, starting in the lower left. Why is this a nice way of doing it? It means that we can represent everything as a binary bit where you can just look at the first bits of the bit heading to identify where is the rest of that data. So as you go to the next level of depth, you add additional digits. So the first digit specifies where you are at the highest level, the next digit, and again, it's shortcutting. It's jumping as fast as possible in that binary way to keep your stream moving really fast. And keyby is actually a beautiful function. It's in there. It's one of those simple things that's, I guess, has been in Flink forever. But it's really useful where we can say, yeah, we're going to keyby these map partitions. And we can even keyby not having to worry about how many we have and what our tile depth is, because we can start at the highest level and we'll just start looking at the first bit, or we can go down to further bits as we add more nodes to a cluster. And we distribute out the data with the number of nodes, and that works fairly nicely. And like I said, you still wind up with some edge cases where you might be downloading neighboring data, but you minimize the amount of it that you ever do. So, hidden Markov model. So this is the basic, this is a best practice solution. It's what you need to do. We made ours explicitly, our implementation of the algorithm is data model agnostic. We can apply it to any vector data. So if someone comes to us and said, you know what, I have my own map for mapping the inside of a building. I have my own map for looking at roads. I have my own map, or sorry, not roads, rivers. I want to look at those. Doesn't matter. Our map matching algorithm will work on it. Just bring that, you reference it, it works. And our ability to our ability to optimize on that, of course, varies on the degree, but we tried to figure out what are the right abstractions when providing those libraries for that code reuse. And as we said, it comes down to, you can find the Markov model, but then emission probability and transition probability are where you really put in the work. So let's talk about paths and points. So what's so nice about this is red, again, is classically what I get from GPS points. I put it onto a path matcher, and everybody actually winds up on the road. And we can do that based on logical paths. This particular example is a center road optimization. I can also say I want to have a lane level optimization. And to go into a little bit more detail. So the emission probability says, what is the chance that any given point could show up on a different vertex on a neighboring road? For example, right here, the most probable point is actually the yellow road going underneath. If all I did was look at one point with no context, that is the best match. But since I know that these are a sequence of points, the emission probability, that one has the higher emission probability, but this has the better transition probability. So that's where I talk about why I'm looking at so many different possible states, as I'm saying, well, you know what? The best chance of getting onto all these roads is here. This is what the probability is. But it's only when I sum those probabilities across an actual path that I really get what is going on. And to give that in sort of, here's another real world example to kind of, so this is the Vertibi algorithm that is being shown here versus, and I'll show an alternative to a greedy match on the next one. But you have these kind of notions where the red points represent what I got for GPS points. This path, this doesn't explain it, but I happen to know the order is going from right to left. So the question is, which road is more likely? And again, if you look at the emission probability, you're most likely to have guessed that it would have been on 202 heading east. However, we know the car was traveling west. The probability that someone was on a major highway in the US going the wrong way on a divided highway, pretty low. It's like being on the Autobahn, going the wrong direction. So we can set internally an internal bound to the matcher. And again, this is the particular implementation we did, but we've explicitly left this open for our internal and external customers to be able to plug in their own implementation, because this is a great getting started. The more you know about your data, the more you can put that into your own algorithm. And again, I would say is a general strategy when processing streams and looking for that. Figure out that logical abstraction where you can allow learning and indication at that level to get it done. So in this case, we're coming from the right and going to the left. So it's coming from east, headed to west. And you can see that early on, the probabilities were way higher than it was on 202. But if we then go to a simple sum of the transition probabilities, what would all those points look, or simply a sum of the probabilities, you can figure out it's far more likely they were on Swedsford Road. Still talking about a 7.4% versus 0.4%. But that's part of how we look into cleaning up that messy data. And here's another strategy. So in this case, we're not using machine learning. We're using deterministic algorithms. When dealing with really messy data, depending on your use case, machine learning may or may not help. We have had no good luck so far with machine learning map matching algorithms, because saying what the right result is based to the chaoticness of the data doesn't line up. We don't have general patterns that GPS points are always off in a particular way. They're off in all sorts of crazy ways, which means that we haven't actually been we find trying to have a deterministic algorithm where we can put things onto what we know about the situation, which is people actually travel on these roads. And this is a good picture in that this here is above the road below. People do not drive their cars off of cliffs. And continue driving. This is just not what people do. And we know that, so we can say, a greedy match would simply look at what was the best probability. And the problem is you only get two of the points only wind up matching out of 4 if you do that greedy match, where it's really clear that those two fit together. But by going on to this other side, we can line up and match through there. And again, this is why I was talking earlier about all of the optimizations on the data, was because I was trying just to get to a point where I could say, hey, let's now make it so the algorithms can play and try out more different options and opportunities and see how they're going to do that. And I can only really make that working in streaming quickly if I optimize that infrastructure of getting access to those data structures as fast as possible. And as I said, there still is no right answer, which is why we have to let people bring in their own algorithms and figure that out. And that's where I come back to our infrastructure story, which is we made accessing that raw data about the geometries as fast as we possibly could. We organized it so we stuck our data. We partitioned our data so that we would have repeated calls being done not only on the same server by doing the tile partitioning, but we'd be likely to be hitting the same L2 cache as we go through that memory of scanning all the nearby roads. Because this is, again, I'm storing this stuff as vectors and integers. This stuff is tiny. You can easily get it into your L2 cache when you want to scan it a few million times per second. And that really helps you get this done. So thank you. That was my presentation on how to kind of make real-time, optimize your streaming for real time with some messy data.
Thank you, Robin. So I believe we have, how long here? We actually have about 10 minutes for questions, so definitely have enough time. Does anyone have any questions? And of course, you can come up afterwards and ask if you don't want to raise your hand. All right, here we go.
So, not being very familiar with your platform that you offer, the example code that you showed, that is something that I could just use in the same way if I were a customer?
Yep.
Okay, because
exactly.
That is actually super interesting, because I've been part of a project that did something similar with their own implementation, and it didn't turn out to work so well. So
all right.
I might give that a try and see how it compares.
Yeah. Again, it's relatively, we just grabbed the data, and we tried to make it, relatively straightforward for what the customer has to do.
Thank you.
Hi, nice talk, first of all. As far as I understood now, even clients has to write code.
Yep.
Are you planning to put come up with a DSL and maybe some particular data structure you think can optimize some of the operation most of your clients do on this data, or you didn't think about that yet?
So there's a couple different ways so far we've gone against trying to produce a domain-specific language for solving these type of problems. And though we have two major use cases that we see on the location processing. One is I have people who compile maps. Industry-wide, the price of getting a map compiled is the equivalent of a couple headcount per year. So around a couple 100,000 per year. There's a bunch of companies who do it around that price point. If you're going to be paying that kind of money for someone to be building maps, you're probably going to hire software engineers who are going to optimize it. But there's a second use case that we have. One of the other parts of our offering is we actually offer a market. We're in the process of offering a marketplace for these data products. And in that case, we are looking at a world where we have people that are more like data analysts and business development who want to do some fairly simple operations. And we're right now evaluating a couple of strategies for doing that. To give you a couple ideas that we kind of talked about, I mean, like I've seen all the SQL options here. One way is representing some of that data as SQL and naming functions. We're finding that many of our customers even do not want to directly send the raw data, as I described in the problems with SDII. They actually would prefer that our platform would at least map match the data, convert it to a point, and then that's the data that they would prefer to trade within the platform. And a couple of the ways we've thought about how to approach that problem is to make default of these processors with config parameters. But when I'm looking at that environment, the kind of people I'm looking at doing are more kind of on a business development side, and so even going as far as a true DSL might be a little too much. But having some obvious config parameters, I want tight matching, I want loose matching, I want to choose which reference map I put it on. Okay. Does that answer your question?
Absolutely, yes. I have another one, though, if I can. Like, the first thing I think when I see a map is how can I navigate it? So if I have, you mentioned SQL, I think what is missing is some, in the standard at least, is some sort of graph function.
Yes.
Are you thinking to,
We offer a variety of graphs, and we ultimately are pulling, if you look at what is the underlying data we do, is one of the layers is not just the geometry, it is a routing graph. And so we have our own routing graph, and that is being used by some of our customers already to implement their own routing graphs. An example of a type of vehicle that has some very different properties, even on our regular roads, is an electric vehicle. How far you can go, energy consumption varies on exactly these attributes, such as elevation, temperature, and those will actually change your range and what your possible routing graph is. And that is a use of our platform, is to develop those specific use case optimization. The other one I give is if you're dealing with routing of something, it's a little different. Let's say boats. There aren't a lot of good solutions for routing boats around streams and canals. There are a number of nicely handmade maps in a variety of environments that are good for that. But if you wanted to make a recreational boating route engine, that would be a lot trickier. And you would have to figure out things like you would come up with very different, this may be discontinuous, but people are willing to walk their small boats 100 meters, but not more. You could produce some really interesting type of stuff with that. And that is the kind of things that our platform is optimized to kind of help people build.
Cool. Thank you.
Sorry, I'll just interject one question. The updates to the map tiles, do you use site inputs for that, or you have your own custom-made solution to bring the updates to the stream processor?
So how do we do that? Right now, we are doing that mostly with site updates or restarts, depending on the team.
Okay.
Thanks for the insightful talk. I'd be interested in the organizational aspects of running your clients' code. So are you basically responsible for operating their Flink jobs in a reliable manner?
That is correct. We take on the responsibility. Again, from their perspective, they upload a jar file. They give us a couple of parameters of how much resource they want. After that, we run it for them. And the right now we're using Kubernetes as our underlying technology for that. But we are definitely, that was very interesting from today's keynote, is that kind of the notion of a Flink library mode would be really useful for us, because effectively we're spinning up one cluster per job right now. We can make relatively small clusters and pack them, but we do a cluster per job. to provide that isolation. And then we can provide network level isolation, then we provide data level, socket level isolation. We can encrypt their data within their, because their JVM is running inside its own container, the storage associated with that can be encrypted with their keys, and we can provide that isolation and security for our customers. It does come at a price of some flexibility. You are not as flexible at being able to schedule your Flink jobs.
If I may, how are the experiences as far as, let's say, resource allocation are concerned? Because you would need to know a lot about the internal logic of a foreign job, basically, to then be able to...
So our pattern is we let our customer execute the code they want to run, and we provide them the metrics on it. Our current business model is we're charging them for the amount of resources they reserve. And so it's up to them to optimize it, and they're incentivized to optimize it reasonably. Again, with various versions of Flink, we have found different issues with what happens on failure and respawn scenarios. We've so far, with our 1.2 jobs, it's generally better if we ever start seeing any failures to suspend the entire cluster and bring it back up again to get the capacity and the performance back up, rather than replace the nodes. I'd be interested. I haven't seen what the numbers have been like on later versions of Flink, but definitely in that time we were not getting good recovery. But we can do that suspend and restart, and that works quite well to be able to get it continuing.
Thank you.
Any more questions? All right. Thank you very much, Robin.